Good afternoon, добрый день, boa tarde. Welcome to Ironbuild, a show where we try to understand how to build a modern database for financial accounting. And today we are going to have a very special episode because if you remember, last week we started to try to understand how queries work, and I really felt like miserable. I wasn't able to make much progress. So my colleague, Raphael, who actually implemented the query support for Tagabital, offered his support. So let's say hi to Raphael and try to dive right into the meaty details. Okay, so Raphael, I guess the floor is yours. Could you explain us how queries work?
Good. Thanks, Glad. So it's a pleasure to be here. Excited to be here at Iron Beetle. And last episode was so much fun. It was like watching someone doing unbox of my code, but the box didn't open. That was really nice.
Yeah, it is always a pleasure to watch someone else suffer.
Okay. We can start from either side. We can start from the interface, so we can cover how queries arrive at Tagapeto, or we can start from the story, how we extract data from Tagapeto. I think we could start from the story because that's the more basic thing. I think that's more didactic. What do you think?
Yeah, I think that's a good idea because if I recall correctly, last time we actually covered at least parts of the interface. I think we started with like documentation and looked at query account transfers and like looked how that gets into like the state machine, and then we got stuck. So let's try to crack this nut from the opposite side. Where should I look for the storage?
Okay, so I guess I have covered a great deal of compaction already. Is that right?
Yeah.
We know how compaction works.
Just a second. There is a comment in chat from Chaitanya that we have an echo problem from your microphone. Do you have headphones? I think that might be to fix the echo. Or you already do headphones?
No, I'm using my microphone here. Let's see how I can change my microphone. I have no idea how things work. Just
I mean, with echo, it is still better than if nobody would have been able to hear you at all. So echo is good, actually.
cool. Is that better?
Well, I can still hear you, so that is good. And let's
Okay.
ask Chai in the chat if it's better. Chai, how's echo now?
Testing my voice. Testing. Okay, that's the right microphone right now.
Yeah. Okay. Let's assume that it works. Regarding compaction, yeah, I think we actually covered compaction to a great depth. So you could.
Cool.
Oh no. Chai says that the echo is still there. Okay, let me check if I do
just
something here. Although I'm not sure if. Okay.
testing.
Okay, so Chai, I toggled something on my side. I'm wondering if that could have helped it. Still hearing it? Yeah, I think. Okay, let's maybe time both these to 3 more minutes, and if we didn't manage to fix the echo problem in 3 minutes, we'll just continue and maybe apply.
Yeah, so it's always painful to set up the audio, but okay. So I guess compaction is a good point to start because in compaction we scan the LSM3 horizontally. We scan a lot of tables, trying to merge those tables into another level. And for queries, we scan the LSM3 in the vertical axis. So we're trying to find across all levels a particular set of keys that are or targets from scans. So both share the same concepts of manifests, index blocks, value blocks. We binary search inside the values blocks to try to find the value that we are looking for. So both are exactly the same at some point. But they start to diverge when we choose the range of key. So scans very often is called range queries because they act on a range. So I think we could start from lookups. So we have a kind of query that's called lookup when we look for a particular ID and you have to find an account or a transfer by this ID. I think we can start from there.
Yeah. The lookup. You mean like lookup, which is just like the forest lookup, which happens in prefetch?
Exactly, yeah.
Okay, so prefetch. Oh. Okay, where?
It's somewhere on the groove, I think.
Let's see prefetch. Yeah, let's see prefetch query transfers. Okay, it's called prefetch enqueue. So if we
exactly inside the groove, we had prefetch.
Yeah, and we pass. Exactly. Yeah, and we pass the key in. So I guess. Prefetch. Well, prefetch from memory, I guess it's less interesting in code path, or maybe it is. So let's see how it works. We have a key.
Yeah, it's less interesting, but still we have some interest points on there. For example, we need to check the top level of the LSM3 is the in-memory table. So we need to check if the ID is there.
So for Prefetch, it's not much interesting because we can just do a lookup inside the hash table. But for scans, we have to actually look inside the array that we have in memory. But still, for lookups, it's not much of interest. And let's jump to Prefetch. I think there is a code in Prefetch that starts reading from disk from storage.
Okay, so it's I think it is called from levels. Yeah, prefetch from level, lookup from level storage. Yeah.
Exactly. Yeah, that's one.
So we have a key, and using this key, we go to the manifest, which stores information about all the tables, and we find the tables which might contain this key. We remember the addresses and the checksums of these tables, and then we go and fetch the corresponding table. So we fetch the index block. Once we fetch the index block, we go and search for this key in the index block. So index block contains so basically index block contains a sorted list of value blocks, and we can binary search for the key in this list of value blocks and find the value block which contains our key. And then we go and read the value block, and once we read the value block, we go and binary search this thing in the binary in the value block. So it feels easy, much easier than it was last week.
Yeah, that's the main idea. So in the index block, we have the range keys. So that's not actually the keys, it's the range keys, the minimum and the maximum key each value contains. And then we guess if the key you are looking for is in the value block or not. We can end up trying to find the key and not find that key there. Or we can find a tombstone if the object was just deleted. But yeah, the main idea is just that. But I have a question now. So we are looking at the ID tree. So TidyHabitu has a LSM forest. So we have different kinds of LSM tree for different kinds of objects. So we have the object tree that holds the account, and we have other trees with the index. So we have one tree for the ID, one tree for code, ledger, user data, and so on. So we have more trees than just one. And in this particular case, we're looking inside the ID tree. And what do you think the ID tree will find when you find that ID that we're looking for? What the ID tree will?
I think, if I recall correctly, our ID tree maps like a big ID, which is like 128 bits, to a small ID, which is a timestamp. So we use ID tree to find a timestamp. And I think timestamp is pretty important for queries.
Exactly. So try to find the file called composite key.
Composite key. Here it is.
Yeah. So that's the building block of each secondary tree. So the composite key contains the prefix, that's the field that we're indexing. In this case, not exactly this case because the ID tree is a little bit different, but we can use the same example here. So the prefix would be the ID, and the suffix would be the timestamp. So the timestamp is the primary key where we're going to find the actual object. So that's an indirection. First, we find the ID. That ID will point to a timestamp, and then we use that timestamp to repeat the same process, but inside the object tree. So we're going to find now the object of that tree. Does that make sense?
Yeah, I think, well, this makes sense for me because I was looking at the code like this before, but I think it might not necessarily make sense for our viewers. So maybe let's try to do a simple example here. So let's say that we have a certain amount of accounts in our database. Let's say that we interested in ID field of an account, like A, and then code, or ledger. So here are like transfers. So we could have, so I'm like, basically I want to show like, want to show an example of like how can we try to find transfers which belong to a certain ledger, which I think is like reasonable thing to do. So let's say we have a certain amount of transfers. Actually, okay. Yeah. And let's say they look something like this. So if I understand correctly, in our like main tree, which actually contains the transfers, we are going to store transfers in the order sorted by their ID/timestamp. Okay, let's actually.
Yeah, we need the timestamp first. Yeah, exactly.
Yeah, let's see like timestamp.
Cool. Cool, much better.
Yeah. So they are sorted by the timestamp, and well, let's do another one, and that creates a problem because it makes finding transfers which belong to a particular ledger hard. So if we are interested in, say, all transfers which belong to the first ledger, we have to fully scan this table. There is no faster way for us to identify transfers belonging to ledger 1 because they are sorted by the timestamp, not by the ledger. So what we do is that we do a composite key which inverses the fields. We first do the ledger and then timestamp. So let's actually, so composite key here would be something like a tuple of 1 and 10. Oh dear, what have I done? No, I don't want to listen to music. Okay. 2, 1, 4, 2, 1. Okay, and like this is kind of like not really interesting thing we did here because we just transposed the two fields. But what we are going to do next, I think, is that we are going to sort by this composite key. And because the ledger is actually the first key, we'll get this fun thing where like now, if we want to find transfers belonging to a particular ledger, well, they are all bunched together. So this is cool. I guess the only problem here is that if we sort transfers this way, then we won't be able to look up them by IDs. We kind of like have only a single way to sort transfers. So what we are going to do is to store two trees in parallel. So instead of like storing this composite tree alongside our transfers, we have a completely different tree here, and this one is sorted like this. Okay, yeah, I think I get it now. This is cool.
Yeah, that's right, exactly that.
Okay, so question is like, what happened in the chat? So, well, yeah, we are figuring this. This is actually like a very cool moment to join Ironbeetle, because I think what we are covering right now is actually, in some sense, the heart of how every relational database works, like how you make the queries work. And if you think about making queries work, like any query in the database, you could execute by brute forcing everything, by just like looking at every object which is stored in your database and matching it against the query, but that is kind of like very slow. So you want to speed things up. And the trick there is that you could actually store objects sorted by multiple keys simultaneously. So in the case of TigerBeetle, we essentially have transfers sorted by their ID, but also transfers sorted by their ledger. So we could look up transfers either by their ID or by their ledger, which is kind of cool. Okay, over to you, Rafael. What should we look at next?
Okay, so now that we know how to look for composite keys, I think we can go to scan3, and that's the next building block that we are interested.
Okay, scan tree.
So scan
Small file
scan tree,
of just
exactly.
1,000 lines of code.
Yeah, including tests. That's why it's so big, I guess. So scan3 is the basic unit that we can scan a secondary tree using a prefix. So for example, in the last example, we want the prefix 1. So we're going to scan any key that's less than 1, 0 until 1, 9999, which will yield for us all the interval from 1 to 15.
Yeah, so this is like marks it. Okay, yeah, that makes sense.
So I think we have a couple functions there that we start scan3 receiving a range, not a range, I think receiving the key plus the timestamp range. Yeah, key min, key max, exactly.
Okay, wait, this is, okay, I'm looking at the K-way merge. Wait, okay, so no, I must say I don't understand it. So if I'm reading this correctly, this key min and key max is fields of a scan tree. Oh, right, because scan tree is presumably a particular scan. So when you want to look for transfers with ledger 1, you create a scan tree where you set key min to 1, 0 and key max to 1 and like infinity.
Yeah.
Yeah. Oh, yeah, right. So we initialize those in it. Okay, yeah, that makes sense.
Plus the direction, so we can scan in reverse order if you want something reversed.
Yeah.
Okay,
I remember when we were looking at the documentation, there was this flags reversed, which controlled the sorting order of the result. But actually, it looks like we are going to push this flag all the way down to the scans. This actually is going to affect the order which we read the data from disk.
Yes, that's right. So from there, it's basically the same as scanning for compaction. So we are reading all the blocks, index blocks, value blocks, but we are binary search inside that range of min and max.
Okay, let's see where it actually happens. Binary search. So this I think is right. It's like inside binary search inside the probe values is the binary search, which is like where the magic happens.
I would
Oh, no.
suggest we just skip that probe part for now because that's for joins. We can go back to probing in the next opportunity, but just
Okay,
to make it
so
easy to understand,
okay,
I
so
think we can go
probably this
to
binary
read.
search.
Yes, this one.
So we read index block, and then we find the blocks which correspond to the key min, key max. Okay, yeah, makes sense. And then we create, this gives us a range of what? Is it like a range of data blocks? Okay, yeah. And then we go and
we start iterating over the value blocks.
Okay, yeah, this is the iterator of the value blocks. Okay, and then we say, okay, yeah, we want to read the next data block. So we go and read it. And once we got the data blocks, that's curious. But why aren't we doing extra filtering here? So kind of like we have like this key range which we are looking for, and I think our block intersects that range, but doesn't necessarily like isn't necessarily fully contained in this range. So there should be some extra filtering here. Where is that?
Okay, so let's navigate a little bit more. So the public API that we expose for scans, first we call read, and then it will be looking inside the store for value blocks that intersect, and then it will call back that we can iterate over the buffered values. When the buffered values is exhausted, we can call read again and repeat the same process until all values were scanned.
Yeah.
I think it's during the read. When we call read, it starts to filter in the keys.
Yeah, I think I noticed my confusion because I switched between files. So right now we are in this country, and then we create this data block iterator. And this next data block isn't actually part of this country. It is part of table value iterator type. So I think, So I think this thing, okay, so we don't have key min, key max here. This iterator just iterates us blocks.
Just walking, yeah.
So I think filtering should actually happen in this data block callback. So let's see if I am correct. Okay, yay! We do binary search. We don't even need to do like filtering. We could actually directly look for what we are interested in. Okay, perfect. So we got ourselves a value block. We find a range of keys which intersect the keys which we were originally looking for, presumably those key min, key max, and then we copy the result somewhere. Okay, I realize like I'm lost in the middle of the woods. So I understand how we got here, but I don't understand where are we going from here.
Cool. Okay, so let's let me think just a second how we can explain that. So after we read the blocks from the grid block, so that memory is just valid inside the callback. So we need to copy that to a buffer. So that's the scan buffer. Every scan receives a buffer from outside. So I think that's the forest that holds the buffer for scans. So we copy that what we found from the grid into that scan, and then we present that to the next layer. So the next layer, you decide what to do with the values that the scan tree found. So remember, the scan tree just found a composite key. So it's not much useful for us because we need the actual transfer. We don't need the composite key for now. So
Yeah,
we need to go to the next level. Yeah.
So before we go, I think I have a question here. So
Okay.
Here in the value block callback, we read a value block. So value block is like 0.5 megabyte. What is the size of this buffer which we are copying data in? Is it like larger than a block, or like roughly as a block, or like maybe it's like, you know, an entire table?
I think it's we have one buffer for the value block and another buffer for the index block, and both are the size of a block. So each scans consume 2 blocks of memory.
Okay. So so I guess it is not that, like, you know, we read a bunch of blocks in memory and hold onto like this whole pile of keys and then get this whole pile to the layer above us. It's our, like, you know, we do like this in a streaming fashion. So we read a block, give it to someone else, and then once we are done, probably we could reuse this memory to read the next block. Okay, this makes sense.
Yeah. So when we read a composite key from that scan, so okay, I read a composite key, it starts with 1, so I know that's ledger 1. And the last part of the composite key is my timestamp. So I'm going to plug that into a lookup. So we have another type called scan lookup, I think. So that scan lookup will receive a composite key produced by some scan tree, no matter which scan tree.
Okay,
and
so just
look inside the object tree.
Yeah. Let's do like a slight pause here, because I feel like I need some like catch up state sync here. So let me try to like repeat this.
Cool.
So okay, let's go back to our scheme. So what I've showed here, like, hey, transfers are sorted by timestamp, but composite keys are stored by ledger, isn't actually true, because transfers are much larger, right? So if we look at it like tie a middle and look at the transfer, it is 128 bytes. So here we also have like a debit account and then like a credit account and like amount and like whatnot. So this basically this here is like huge.
Huge, exactly.
Yeah, and while here actually I think I draw a picture which corresponds to reality pretty well. Like, we only store composite keys. So like composite key is the entire value which we store in the database. So if we are looking for transfers of ledger 1, we go here, we read this block, and we see, okay, so the first transfer with ledger 1 has timestamp equal 10. But this doesn't actually tell us, like, you know, debit account ID, credit account ID, nothing else about this transfer. So now we should take this 10 and go back to our full tree, where we could now go and find the entire object. Okay, so now I think I've caught up. And where should we go next from our scan tree?
And try to find the scan lookup. I don't remember the name of the file exactly, but I think something.
Okay, so
related
we have
to
scan lookup type defined in a
scan.
file called scan lookup. Very
Cool.
good name here,
Okay.
Rafael. Very easy to find.
Cool. So scan lookup, it receives a different type of scan. It's not directly a scan tree. I'll explain why in just a second, but it's a scan. So scan is an interface. It's abstraction over scan tree, because scan lookups are over the entire group, entire object. So I create a scan lookup to look up for transfers or accounts or balances, whatever. And I receive index from any field that they are indexed. So for example, I can look up a transfer for code or for ledger or by user data. So no matter what kind of field I'm looking for, I'm using the same, exactly the same scan lookup. So that's why scan is just an abstraction over the scan tree type. The scan tree type is the concrete type that will look inside a specific tree. So it's look inside the fields, codes or user data, whatever. So that's the difference here. And the scan lookup has the job to scan over the object tree, looking for that timestamp and result in the object. So it's basically do what we just saw by ID at the beginning of the video.
Okay, yeah, I guess it makes sense. So let me try to repeat it to see just how wrong I am. So our scan tree type is parameterized by a specific tree. What is a tree? Well, if we look at our transfer again here, it has a bunch of fields, and actually, like more or less for every field here, we are going to have a separate tree. So we're going to have like one main tree which contains transfers, but also we'll have a tree for ledger which contains these pairs of like ledger timestamp. And similarly, we are going to have a tree for timeout, a tree for amount, like whatever. So for essentially for every field of a transfer object, you are going to have a separate scan tree type. And then when you actually are scanning for transfers, I think you might also do things like, hey, I want to find all transfers which belong to ledger 5 and simultaneously have code 17. So you actually want to take like two scan tree types and turn them kind of like into like the intersection to fetch the scans. So that's why our scan lookup is parameterized by the group. So scan tree, there is like one scan tree for every field of a transfer. But for scan lookup, we have only one scan lookup for objects. So we have scan lookup for transfers and scan lookup for accounts. Is this roughly on the mark?
That's perfect. I think you are ready now for the scan, so we can look inside the scan, see what we have there.
Okay, where it is defined?
Unless
I think it is in the scan builder, right?
Scan builder, it's a level above that, but we can find the reference from there.
Okay, scan.
Scan is the scan type. Yeah, exactly.
So
the scan type is
it is in scan builder. I remember that. Then scan is defined in scan builder. Okay, yeah. Let's see.
Cool. So the scan type it's a tagged union at the end that contains each tag contains the implementation of the scan tree for each indexed field that we have for a particular object. So for example, for transfer, we have the ID tree, we have the code tree, the ledger tree, the user data tree, and so on. But we also have three special tags that are merged. So we have a merge for intersection, a merge for union, and a merge for minus. In that case, it's a negation. So we have three different merge algorithms that you can combine all the different scans. So yes, we can do, for example, I'll transfer that ledger equals 1 and code equals 2. Or we can combine that using not union, we can not intersection, we can use union. Every transfer where debt credits are equals 1. So we do that using OR. So we can translate that for OR and
Okay. Okay. I think. Oh, this is a big brain. But I think I understand this. So let me maybe try to like read this code. So as you said, like this, like scanning is essentially so. We established that for every field of a transfer, we have a separate scan tree type. Now we want to create an atom essentially which can hold either of those specific trees. And of course, we are going to use Zig mirror programming there. What's more, we also say that, hey, actually, in addition to like primitive scan tree types, we could also do union, intersection, and difference of two scan trees. So essentially, not only we have like in our big union a variant for each tree, we also have like this special variants. And this, I think, is what we are going to do. So this dispatcher, if I'm reading the code correctly, is going to be our big union. And this, I love this. Like this is really, I didn't realize that this is possible. So what we are doing here? Well, first we do a union which contains only those like special cases. So merge union, merge intersection, merge difference, and then timestamp. I guess timestamp is, yeah, so timestamp is the object tree. So timestamp is like the thing which will allow us to get the actual objects. Okay, but then we kind of like want like, you know, to like extra fields here. Like, you know, if it were Rust, we'll like, you know, do like some horrible proc macro here, and it will like just inject like a bunch of code.
Inject the code.
Yeah. We can't really like augment existing types in Zig, but looks like we are kind of like doing like quasi-ported thing because we aren't actually using this type. You see, like the only usage of this type is that we pass it directly into type info. So we want to know like which parts comprise this type, but we don't care about the types. So okay, so essentially type info is a thing which we can turn back into a union atom. But before we will turn it back into union atom, we'll actually go and add our extra fields. So we add the ID field, and then we add a field for each of our fields we have indexes on, and then we do, oh, and then I think, wait, what's happening here? We need a tagged union for dynamic dispatch. Tag type. Oh, okay, right. So I think this is because like in Zig, like union atom is actually two things. It is a tag type and a union type. So when we manually adjust this thing, we need to augment both the tag type and the union type. Actually, okay, I'm wondering, like if I just do this, what will break? What happens if I don't?
Good question. No idea.
Let's see. Like do we? It would be fun if it compiles. Oh no, it doesn't compile. no field name ID in. Okay, yeah. So it like Zeek properly checks that the two are actually aligned. So okay, yeah. I think oh, this is brilliant. But I think I got it. So this dispatcher is basically like a union of all possible scans, where like some scans
Mhm.
are just primitive tree scans, some scans are special, like our timestamp or object tree scan, and some scans are like mergers and intersections and whatever. Okay, yeah, that makes sense.
Awesome. So now I think we can visit the scan builder type.
Okay, scan builder type. Yeah,
Cool. So the scan builder is
this is a thing which like
this scan builder.
like really got me scared like last time, because I was like, oh dear, like.
Yeah, I think
But now
we
I'm not
start
afraid.
by the most complicated part, so it was a good choice for starting with. But okay, let's tackle that now. So the scan builder is like what? How can I put that? It's like our query plan. It's not exactly a query plan, but it's how we can build together all this type of scans. So, for example, we receive a buffer. It's the forest that holds the buffer. We have just a limited number of scans that can run at the same time. I think that's 6 for now. We can have at most 6 fields in our queries. So it's the limits that we have for functions like get account transfers, for example, where we use 6 fields at the same time. And the scan builder allows us to combine together different scans using intersection. So we can do and using union, we can do or we don't have minus implemented right now, but yeah, there is interface for that. So let's try to take a look of the functions in that
So
slide.
I think well, maybe it is possible to think about scan builder as like SQL syntax. So it is not like the planner of the queries, but it is actually how you express this like hierarchical nature of queries. Like you could see, hey, I would like to scan transfers where code equal 1, and I would like to scan transfers where status is posted, and I want like the intersection of this, and then like give me actual transfer objects. So yeah, this is okay. This is wait, is this like compiler? Like this is really like syntax tree. This is actually something I should be very well in comfort with. But well, okay. Let's see. Let's see at the code. So how do we construct scans using scan builder?
Okay, so let's start by the other side. Let's see the prefetch for that code that we use the scan builder. Let's take a look at the prefetch for get account transfers inside the state machine.
Okay, let's do this. State machine, prefetch account transfers. You say, right?
Account transfer, that's
yeah,
the most complex that we have.
Okay, prefetch get account transfers.
Okay. Just a second, our screen is just refreshing for me. I can't read the code yet. Okay. And I think there is a function called get scan from filter. And please
I remember.
Yeah, get scan from filter.
Yeah, I remember that one. Okay, yeah.
Yes, that one. So that's where we validate the filter if there is some missing fields, and then we start building the query that we want using the scan builder. So that's the logic where we try to mimic the Cairo plan and build the actual query.
Okay, so let's take a look here. So, okay, if we say that, hey, if we looking for transfers which belong to particular debit account, we say, okay, we do scan on debit account ID with this account ID. Okay, that makes sense.
Mhm.
And
And we start to store that inside the array of scans.
yeah,
We're
we
not
have like
doing any merge yet. Yeah,
yeah. So we kind of just
it's
like
just
remember those like scans, and yeah, we indeed can have like at most 5 of them.
mhm. We're just building a bunch of disconnected scans for now.
Yeah.
And at
Now,
the very end, we merge them together using AND.
yeah, this is fun. So if we only do one, so if we only look for only for debit account or only for credit account, we do that. But if we are interested in like both credit accounts and debit accounts, oh, we actually do a udent here. So this is or, this is not an and.
Yes, yes, yes.
Okay,
Because
yeah. Oh,
we can
well,
look for either
yeah. Okay,
side of
okay.
the debit or
Yeah, yeah.
credit.
This makes sense. So basically, this is like we want to find like all transfers which involve this account either on the credit side or on the debit side. Okay, yeah. And then we have a bunch of different scans. So we could
Mhm.
filter by user data and code. And wait, can we actually filter by ledger? I'm not seeing ledger filters.
Yeah, no, in that case we can't because account ID is required and the account has ledger, all right? But for query
Oh,
transfer,
okay,
we can scan
okay,
for by ledger.
okay. Huh. Wait. Well, oh, okay, right. So yeah, we are like in this case we always have account ID. So all the transfers
Mhm.
we will look up will belong to a particular account. This query will never ever return transfers from like different accounts. So they actually must all have the same ledger. I wonder, do we have an assert here? Like when we finish the transfer, do we assert that we all have the same ledger? This is actually a non-trivial business invariant here. That's fun.
I don't think so because we don't inspect the result of the query each
Yeah,
value, but we have tests for that, but not during runtime.
yeah. We might actually add this like under like constants verify, because it
Yeah.
feels like fun condition to check. Okay, yeah. So we got a bunch of these conditions. Oh, okay. So actually, this is
Mhm.
okay. So I now see the structure. So we have and three that was not an English word. So we have like and inside this and we have or
Yeah.
credit account ID equals a debit account ID equals a, and then like it's code equals C user. It's not SQL. I don't have to caps locus user data equals Y. Okay, so this makes sense. We have like this like nested structure where we have like and or, which makes me think about whether TAG-ABTOOL is already Turing complete. But yeah, okay, this is cool. So we do, and then we like do this like merge intersection. Presumably merge intersection is cool because it is not pairwise intersection. It actually takes all the scans and intersects them. Okay, yeah, that makes sense.
Okay, so we just built our scans with many complex conditions up to the limit of max scan. And what each scan of those will result. So all scans have one thing in common. So they all are going to result the same timestamp. So all the scans, so it's a scan tree or it's a merge scan. So they're all together resulting the same, not the same, but the timestamp referring to the same object tree. So the intersection of all those composite keys and so on, we are going to get a string of timestamps that we can look inside the object tree.
Okay, yeah, makes sense.
That's why we have a condition somewhere that tells us that there is no other condition we need to scan by the object tree by timestamp. I think that's the query transfer function. We have this comment there. I remember that from the last episode.
Execute profession query transfers.
Yeah, let's see the get scan.
I think it's like scan
Get scan from filter some.
Or account filter. I think it should be. Well, no. Scan from query filter. This one.
Yeah, this one. So the timestamp range, it's embedded inside the composite key. So if I want timestamp from today and from yesterday until today, I can express that inside the key. So I can just scan ledger equals 1 and that timestamp range, because the timestamp range is part of the composite key. But if I'm not scanned by any particular secondary index, just by timestamp, I don't have any choice. I need to scan by the timestamp field that's present in the object tree. So that's one edge case that we have for scans.
Okay. Yeah, that makes sense. So I guess. I guess the question is like, Raphael, like, how do you feel for time? Like normally, like I do this episode for about an hour, and we are at an hour, so we could maybe say that, hey, we arranged it here. But like, if you feel like, hey, let's do more queries, we could just like continue. I don't know. I have a concert
So,
tomorrow at 9 p.m. So we have like almost 24 hours left.
So no, it's a pleasure to be here in the next episode, so we can do that again. So no problem. We can stop now and resume in the next one.
Oh, okay.
That's fine.
Yeah. Okay. So that's then let's do it, because I think we are actually like at a nice place because we kind of like understand like the API, like what scans should ultimately do. We understand like the low-level representation, so how the data is laid out on disk, and like roughly how a single scan tree works. And we know how we construct this like tree of scans, this expression which says like, hey, actually we want to like get this data out of it. What we are missing is like the logic to actually drive this whole machinery, to actually evaluate all those and or conditions and 50 things around. Like this is where like those like magical words like zigzag merge probably are going to be uttered. And that feels like, yeah, it's a good place to leave for next episode. Okay, so
Yes. Just one brief thing that I remember. And the last episode, you said that okay, we don't have account field on query transfer thing. So you just look at the query transfer filter, and you missed the account ID there. So I remember that. So you got very confused by that. So now I think that starts making sense because we don't have a complex way to represent or and ends. So query field, yeah. So there is no account ID on that filter.
yeah.
That's because we don't expose yet an API to do intersection or unions, and that would be very complicated to express. You want the account ID to be the debit side, the credit side, both using or different of each one. So I can have any debit side, but that specific credit side. So we don't have that complexity yet to express the query API. But for now, we have just a limited set of query filters that you can execute.
Yeah. Okay, makes sense. But we still have like query accounts transfer where like if you want for a specific account, you can do this. Okay, makes sense.
Yeah.
Okay, let's call it. And also today, I really feel like today we've made like 10 times more progress that we did last time. So thank you very much, Raphael, for offering to join Aramidal. And I bet in exactly 1 week minus 1 hour at 5 p.m. UTC, we'll meet again to continue learning how to actually execute query. Thanks everyone for watching it live on Twitch or for watching it on YouTube, and see you around. Goodbye.
See you.